before we do the infinite dimensional example, let me just mention that everything we did was for separable data. It's very easy to accommodate non-separable data. Now, in the primal form, we said that what we're going to do is minimize W transpose W1/2, plus the margin penetration C sum from n equals 1 to big N of Cn. And the separation condition was that Yn W transpose Xn plus B should be greater or equal to 1 minus Cn. Okay. And C was the regularization parameter. It turns out that almost exactly the same dual algorithm works with the same inner product property. Okay. The only difference is that the constraint on alpha n becomes C greater or equal to alpha n greater or equal to 0. So this regularization constant C becomes an upper bound on the alpha n. And then the definition of a support vector is not just that it must be greater than 0. So a support vector must be greater than 0 and must be at most C. So in other words, the constraint, none of the constraints are saturated. That makes it a support vector and exactly the same. So that's almost a non-change. So you can do non-separable data by introducing the soft margin, okay, and the optimization problem in the dual space hardly changes. Okay, so that's just a quick note about non-separable data, non-linearly separable data. You can use the soft margin hyperplane. Okay, so let's get back and do this infinite dimensional example, and then we're done. Okay, so consider the following transform into an infinite dimensional space. You can think of this as an infinite order polynomial transform. So x goes to e to the minus x squared. Okay, and now I'm going to do, basically x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, going on forever. Infinite dimensional polynomial transform. Well, the algebra is going to get messy. So I'm going to insert some constants into these that make things a little bit more manageable. So I'm going to put a square root of 2 to the 0 over 0 factorial. Okay, a square root of 2 to the 1 over 1 factorial. A square root of 2 to the 2 over 2 factorial. A square root of 2 to the 3 over 3 factorial, and so on. You get the idea. The kth order power, x to the k, will have a square root of 2 to the k over k factorial. Okay, so, wow! Should be looking at me and saying, are you crazy? Okay, you're going to go and transform into this infinite dimensional polynomial space. It's not possible. Yes, we will never have to physically do that. That's the whole point. That's the game in town. Okay, that's the miracle. Okay, so this is z. Okay, so this is z. Let's consider what happens if I have another vector, x prime. This goes to e to the minus x prime squared. Okay, square root of 2 to the 0 over 0 factorial x prime to the 0. Square root of 2 to the 1 over 1 factorial x prime to the 1, and so on. Square root of 2 to the k over k factorial x prime to the k. Okay, so this is z prime. And if I were actually to go into this space and compute the dot product, okay, z dotted into z prime is equal to e to the minus x squared, e to the minus x prime squared. These turn out to be important. That normalizes this whole thing. Okay, it keeps this under control. Otherwise, it's blowing up. Okay, so this e to the minus x squared, e to the minus x prime squared. I'm taking the dot product. So this times this. Okay, times. Okay, the component-wise multiplication, and then you add the dot product. Okay, so this times this. That's the beauty of this square root term. The square roots disappear. So I get 2 to the 0 over 0 factorial x prime to the 0. So x prime to the 0 plus 2 to the 1 over 1 factorial over 1 factorial. The square roots cancel. X prime to the 1 plus 2 to the 2 over 2 factorial x prime to the 2 plus going on forever. But we are all experts at analysis, and we notice that this infinite sum is always convergent, and it actually converts. So this is, we can put the 2 to the 0 in here. So let me make this 2x prime. 2 to the 1 can be brought in here. So let me make this 2x prime. 2 to the 2 can be brought in here. So let me make this 2x prime. So you have something to the 0 over 0 factorial, something to the 1 over 1 factorial, something to the 2 over 2 factorial, adding it all up. What is that? I'll give you a couple of seconds. We know that sum. It's a famous sum. Okay, 1, 2, 3, 4, 5. I hope you all said this is just e to the 2x prime. So this is e to the minus x squared minus times e to the minus x prime squared times e to to the 2x x prime. Well, from basic high school algebra, this is just e to the minus of x minus x prime squared. What a simple function. What a simple function in my one-dimensional space. So this is a one-dimensional x. What a simple function in my one-dimensional space that computes the dot product in this infinite dimensional space. This is allowing me to perform learning with infinite order polynomials. Wow. This is called the Gaussian kernel. And so, like I said, the game we play is, ideally we would like to say, let's construct a feature transform and the corresponding kernel. Usually that's the wrong way to go about it. Sketching your nose the wrong way around your head. I can't do it. Okay, we don't do it that way. Usually what we do is we say, let's just dream up a kernel. I'm sure it corresponds to some z-space, and I don't need to know the z-space, because why do I need to know the z-space? I can do the entire algorithm without ever going there. That's the beauty. So with this kernel, I can do infinite dimensional polynomial regression. This is called the Gaussian kernel. It computes a dot product in an infinite dimensional polynomial transformed space. Okay, the general version of this, so this is for one dimension, the general version of this Gaussian kernel is, so k of x, x prime, k of x, x prime. The kernel that gives us the dot product in my z space is, in this case, it's e to the minus x prime squared. Okay. And the general Gaussian kernel, k of, if these are vectors in some original d-dimensional space, x prime is equal to e to the minus. We allow a gamma term, a gamma factor. You can multiply by a constant. Okay, the distance between x and x prime squared. This is a special case of that distance. Okay. So this is the Gaussian kernel. It corresponds to the inner product in some space. Okay. And using this kernel to replace the dot products in the optimal hyperplane algorithm, which was only possible because we spent all that effort to go into the dual space and recognize that that algorithm only depends on inner products. Wow! Okay, that's the power that it has opened up. That's the world that it has opened up. The ability to now forget about that feature transform space and simulate it with a kernel. That's all that's going on here. And we have lots of kernels now, and we sometimes don't even know what feature space it corresponds to. We can just prove that it corresponds to a feature space. So there's a theorem called Mercer's theorem, which says that as long as you dream up any kernel you want that's symmetric, so if you flip x and x prime, you get the same value, and it's positive definite. Okay, so you need to know what positive definite means for functions of two variables. Basically, it corresponds to the fact that this kernel matrix, this Gram matrix that is defined, is always a positive definite matrix, okay, no matter what the data points are. Okay? So as long as your kernel guarantees those two properties, it does correspond to some feature transform space. I don't know what it is, but who cares? Okay. So let's summarize. And this is a real miracle. We can do learning in infinite dimensional spaces now. Infinite dimensional spaces. Okay. Summary. It's computationally feasible to learn in infinite dimensional spaces. It's computationally feasible to learn in infinite dimensional spaces. Okay, and what's the idea here? That's because we have the kernel, which takes two arguments in your original space and gives you the dot product in your feature transform space. And the ability to compute dot products in your feature transform space is the only thing you need to run the optimal hyperplane algorithm in that space and even produce the classifier that runs in that space. The classifier also only needs the ability to compute dot products. And the kernel is this magic mechanism that allows us to compute that dot product. Okay. And we all know that if you go and learn in infinite dimensional spaces, okay, you had better watch out because it's non-falsifiable. You'll always be able to separate the data. So you'll always be able to separate the data. Okay. In other words, you've lost all control between E in and E out. And so you have to regularize like heck. Okay, so you have to regularize. And that's where we come full circle. That's the beauty of the optimal hyperplane. It maximally regularizes. It's the max margin. Okay. So the only thing that allows us to get away with jumping into this infinite dimensional space is if, the maximum margin constrains you enough. So even though you technically have the ability to do arbitrarily complex separators, you have to regularize and get this maximum margin guy. And effectively, if the number of support vectors is small, that means you've effectively used a few degrees of freedom, even though you had infinitely many. And so if you've effectively used a few degrees of freedom, that is what brings E in and the E out issue back into perspective, brings it under control. And that's because we can control E out with parameters that are not directly linked to the dimensionality of the space. So this will be okay. So we survive when number of support vectors is small. So even though you started with huge capability, you only use a very small amount of that capability. Okay, so two things needed to come together, and they both come together with the optimal hyperplane. What are those two things? It has to be computationally feasible to go into infinite space, in infinite dimensional spaces. It's computationally feasible as long as you have an inner product algorithm, and this happens to be an inner product algorithm. And any inner product algorithm can be so-called kernelized. Okay. But that alone is not enough. Okay. That just, allows us to go into a huge dimensional space and efficiently perform the learning. Doesn't mean that the learning will work. For the learning to work, you have to have this maximum margin, this maximum regularization. You have to not use all that power, even though it's available. Use only the power you need. Okay? Become maximally robust to measurement error. Okay, and so I hope that I've given you a flavor for how powerful the optimal hyperplane is. And what is the optimal hyperplane? It's just a hyperplane. It's a linear model. Didn't I say the linear model is so powerful? Watch out for the linear model. You cannot solve your problem with a linear model. You haven't thought enough about the problem, but now we've given you the nonlinear feature transform, and we've even given you feature transforms into infinite dimensions with the ability to control. You don't need much more. Checking out.